We're live. Welcome to today's Wolfram Institute live stream. Today we're joined with Nik Murzin, who's been working on some string diagrams for lambda calculus terms. Doing some live coding today. So, Nik, go ahead.
Yeah. So Steven recently, like a month ago or so, together with me and William, wrote a piece about lambdas and just exploring in general what those objects, computational objects are, like drawing a bunch of cool diagrams, pictures, graphs, trees, and so on. Right. So he already talked about it in some 2 hour long video, like going through all the block. So I'm gonna try to not to in intersect a lot of it. So to try to be more go into some other direction, exploring some other fields that haven't been unexplored, like some live coding, specifically maybe some diagrams. So that's why we called it like string diagrams. They were we just briefly explored during the blog writing. We were briefly exploring these objects that will come around here, right? So these objects, I was working for them a little bit longer since then, right? This is but let's just start a little bit from the beginning, just as a recap, I guess. What are lambdas? All right, so yeah, it comes with a packlet. So we have a packlet developed with all the functionality that included in the block, like all capable of all the visualization and reduction, enumeration, sampling of lambdas, and like representing them in all kind of formats, even with the weird ones. But yeah, mostly visualizations, right? With a bunch of examples. So you can install it like that, load it like that, and you have a bunch of symbols coming together with this packlet, right? So basic ones, of course, are like some enumeration, so that we can see what the actual objects we are dealing with. What is it? Enumerate lambdas, for example. I think it. Now let's just try size. There are different ways to enumerate them. Size in terms of how many leaves the underlying expression has. So lambdas together with the variables. And the variables are encoded with integers that we call De Broglie indices. So for example, this lambda, which is of course lambda expression is of course just a anonymous function, right? So we have for more direct Wolfram language representation, for example, you can turn it into a function. So this is like a Wolfram language function that takes an argument called a and returns another function that also takes another argument and returns it immediately. So this is like an identity function, and we just made a function that returns this identity. And this one here represents this particular variable. It represents the depth of the variable. So it basically references the variable of the closest lambda. So this one links to this lambda, and that can be represented by this diagram more easily, I believe. Like that, we call it diagram smiles. So this shows in colors which variable references what. And I think if you want the more abstract one with the Broglie indices, you can disable variables. If I would remember how it is done, I think there's an option for that. Something like arguments. Yes, arguments goes to false. False. Maybe it has to be a string. How it worked. Yeah, actually. Okay. So that's another way without actually naming the variables, just the integers. You can represent a lambda expression like that. So we have this lambda expression, we can enumerate them, visualize them. There are, of course, other diagrams, like I think I have a separate one. Anyway, I have lambda diagram. Let's just keep exploring this one. This is very simple one, maybe not that and illuminating what does it do, but in a way that
So
shows all
which
the
one's the A
lambdas.
variable in this case?
What is a variable? I think it's that line here. I think you can do something like did it like that? Oh, this highlighting, it's good. Well, maybe. No. There's a cool, I forgot, I renamed all of them at the end. There's something like labeled tooltips. Tooltips can be useful so that we can, yeah. So these are two lambdas, so we kind of frame them. This is the inner lambda, this is the outer lambda, and this is the variable one, right?
Okay.
So if we want for example, if we had a more complicated expression like that, when we apply this variable to itself, then we'll have to represent also an application. That's the first time the application comes into representation of our expression. So this is the application. So this is the variable. Let me put the tooltips on by default. Maybe. Got this done. I think that would work. Right. Okay. So maybe even also, what was the other one labeled? Let's try that one. Okay, you can see the lambdas here without any mouse overing it. So that's the application, that's the variable, that's the same variable. That's why it's emanating from the same lambda. So in a way, this horizontal line represents the lambda expression. It's the lambda body, like the abstraction, lambda abstraction itself. So when some variable is referring to this lambda, we emit like a vertical line for a variable. And the application is another horizontal line. So in a way, this application of one applied to one is this application here, right? It's not a canonical Tron diagram, but there's a way to turn it more into more canonical one. There are a few options for that. You can make it like thick. You disable all the dots here, all the labels. And I think the canonical Tron diagram is like this. Labeled, right? Yeah, like this. It's like more pure lines. Like let's like try some more complicated one. Just see how to random lambda, maybe size 10, something like that. Right? So this is like a more canonical lambda diagram. And you can explore it interactively. So there's like all the tooltips already there, but you can make it dynamical. I believe it's like there's a did I do it like with this plot? Trying to like this plot interactivity. I think that's will make it dynamic if I remember correctly. And if you also make it colored, it would be more apparent. So there are many options for visualizing this stuff. Okay, this is like a boring lambda, but sometimes, oh yeah, no, there's no separate color for that. But there's some lambdas here, some horizontal lines represent just application, like this variable 2 applied to 1 or this 2 applied to 2 there. But some of them represent lambda application, and that's the main object of the lambda abstraction. That's where the magic can happen, and the term can be reduced and rewritten to another term. And I think if you make it interactive, you can click on this, right? So whenever you in the tooltip you see this lambda application, when this some body of the function lambda body and its argument come together and apply, you can perform the substitution, the reduction, the beta reduction happen, and you can rewrite the whole term and turn it into something else. In this case, it's actually nothing happens because there's a quine in there conveniently. So it's like this lambda 1, let me write it down. This one is the quine. So technically you can rewrite it because there's a lambda being applied to some argument, which is basically the same body. But if you try to reduce it, it reduces to itself. But technically reduction happened. So that's why it's like lambda application, I click it and it's just nothing happens. Right?
That's
So
a fixed point in the beta reduction.
Yeah, it's the fixed point with like period 1. So it immediately writes. Sometimes there are more periods, like there may be cycle for multiple terms until it starts repeating itself. But yeah, the fixed point. the smallest one possible, I believe.
So the basic
If
idea of
you
like a lambda expression is like you have some variables as input, and then you're taking those variables and you're putting them into certain leaves on a tree. Is that accurate?
in a way, yeah, it's like you can try to mimic what is it going to do. So this is the lambda, this is its body, right? We can try to handcraft this better reduction. So we take the body, this is the argument, right? So we can like this is the body,
Yeah.
this is the argument. And what happens is you just replace each because this refers to the argument because it's depth1 variable, it refers to this variable. So you have to substitute this argument for all of the variables that references it, right? So that's what it does. So now you can do that, and you get the same thing back. So that's like a simple substitution that happened. And that's the whole rule of the lambda calculus, untyped lambda calculus, so that's every lambda expression contain this better reduced reduction terms, and you can reduce them. Sometimes they terminate, and you basically or have a fixed point or terminate, and there's no better reduction happen. They can just blow up. And in the block, of course, we have a lot of examples of this happening, right? So I'm not gonna like unless someone wants to explore this a little bit further somehow. But we have like a lot of examples around it. Like this kind of plots conveniently show and visualization what's happening. Like this is the initial lambda. You start reducing them. There's a term highlighted, right? And the next highlighted term is the next one, and so on, right? And it goes and it just explodes in size. It just constantly grows, right? So
But is that beta reduction being applied to this?
yeah, that's the only rule you should care about. Of course, there's some other rules like eta reduction. Uh, I don't even remember how it's like. We have eta reduce. I think it's basically about um, something like if there's a. Let me try to do something. Uh, it's like what is it doing? It's supposed to get rid of some identities or something like that. Yeah, I think like whenever you have something like this.
It reduces lambda x dot mx to just m if m doesn't contain x. So an example you could try is lambda 2 1.
But this one, this is example, right? So we have this term applied to itself to one, right? So in a way that's equivalent to just taking the one. So this is identity being applied to some argument.
Yeah.
So it can be reduced. It can be better reduced because well, it can also be better reduced, but
yeah, an example that cannot be better reduced is lambda 2 1.
lambda 2 1 like that, right?
Yeah.
Sorry, just for the sake of the YouTube viewers, we might want to do an extra zoom in on the notebook for this stream.
Thanks,
Maybe
James.
try
Yeah.
200%.
Already 150, but we can do 200.
Nice, that looks good.
Okay. So yeah, so that's an example of that reduction. We don't really care about this rule too much, but yeah, we can technically do it. But the main actor here is better reduce. So and that's mostly what we will be exploring, trying to perform better reduction on all of this differently sized lambdas after enumerating, finding some weird creatures, with some weird looking diagrams and behavior. But yeah, but what I wanted to get a little bit deeper today is to explore this sort of diagrams, the string diagrams, because it was mostly unexplored when at the moment of the block writing, but I've been trying to like improve it a little bit since then. Maybe in some degree, maybe in some day it actually got worse, but yeah. Like for example, let's see what it actually. Let's try to first understand what's happening here. So this is using other Packlet I also included in the instruction count installed. Let me start putting it here, right? So let's do string diagrams. So this is like this is the Packlet that is under development currently, which is trying to represent all kind of diagrams in general for like for the purpose of like doing many maybe like category theory of monoidal character, so to speak, when you can compose them in many different ways. Actually, just two. You can like put them together, which is called like diagram product, or you can compose them side by side, doing by diagram composition. So in a way, it's a different way of making diagrams, not like a graph, like you usually do, or hypergraph when you try to specify some edges and vertices explicitly. Here you specify pieces that look like edges, hyper edges, like with some number of ports and some edges being completely implicit. That's like those wires are not specified by the specification of the diagram. They try to be recovered from the way you compose them together, so to speak, right? So, and you can construct these diagrams. So there are a bunch of applications for those. You can make quantum circuits. Those are one example of diagrams. You can just represent functions because you have a composition of functions, right? You can do maybe some system models when you have actual electric circuits, perhaps with all the resistors, capacitors, and all that. Maybe molecules. Those are not very interesting because they're just basically graphs because we have bonds. But lambdas are very minimal examples when it already becomes quite interesting. So when you make a lambda into the string diagram, so essentially each lambda becomes this particular node with one output wire or port and two input wires. Actually, it's like one input and another one, kind of an input, but the wire goes in a different direction. So in a way, maybe it's two outputs. So one represents the binding or the body or something like that. Another one is a variable. And you can see that actually each variable is always going to be represented as this U-turn in the diagram. So there are two variables, and we have these two U-turns. I think let's just try not the smooth one. Smooth. There's a bit. Yeah. There is some additional smoothing step happening to just more explicitly see what's actually happening. There are some cool options that you can provide to see what actually this diagram is built of, which blocks it is constructed from. Maybe all like that. So you can see like this. Now you see that this whole diagram as a grid. So each cell contains sub-diagram node in it. So even this one, which looks like a piece of wire, but in order to lay it out in a nice grid, we have to represent this special type of diagram, essentially like an identity diagram, which is just a wire like that. So in a way, piece of wires are also diagrams, and there are some specific rules how you should manipulate these diagrams, which are essentially wires, like these identities, or there are some like permutation diagram, for example, which may be like P and A, when you just swap around, maybe BA, CA, something like that. When you just have some wires crossing each other, which is just strings. So that's where the string diagram name is coming from. You have these special diagrams that look like string, and when you compose them together in some larger diagram, there are some special natural rules that you can apply to this diagram by manipulating these wires as strings. Basically, you can move them around, right? Of course, when you do this like a grid, they don't very flexible anymore, right? So, for example, by default, actually, when you do this, not the lambda string diagram, this comes from the lambda Packlet, so it already knows what lambdas are to some degree, right? But there is a more raw functionality to, let's actually not do for the lambda, but some simple expression like f applied to 1. Here, if you make an arbitrary expression into a string diagram, it actually makes something like a graph. Not very good embedded graph, because it's not, it contains vertices and edges, but now you also care about the orientation of each vertex, right? So that's why the default embedding is not so good. It like introduces this weird crossing of edges and so on. But the idea is that yes, there's when we have this application, like in Wolfram language terms, there's a head expression and its argument. You create a special application node, and on the left it's going to be its head, which is f. It's on the left here actually, because if you ignore this swapping going on, and the argument is on the right. So you can, if you have more than one application, like two, you have two applications now. And if you track down what's happening, there's one. This is represents this one applied to two, and this represents this whole thing being an argument to f, right? And so
That's
this is like,
interesting. So, like, what if you did like F1, 2, 1, 2 instead of a double application?
I think this in this case, yeah, I think it handles it, but now it's like application. It has three inputs. So the one on the left, the most left input is always the head, right? So you can represent it like that. But that's for arbitrary expression. For lambdas, there's no actually multiple arguments. There's always a single argument. For arbitrary lambda term, you only have single arguments, so you don't care about this case. Your application nodes are always single output, two inputs, single output, like that, right? And there's a special rule for lambdas. So if you go for lambdas, it's actually gonna know, it's like there's a special rule for lambdas. It's not no longer treated as f. So now it's it also has an output, but the variable now is like a U-turn, because you need to bind it. So in a way, you directly embed its variable form, because this De Broglie index is like, for this identity function is like this. So that's, in a way, you have x appearing twice. So that's why they're the same thing. So the same wire, because it represents x. One is going in and another is going out. Okay.
It's like it's calling
So
out for
if you
its
have
input. Lambda has an input
Yeah,
x, and that x goes back into lambda to the output.
in a way, yeah, something like that. You just have to. The only way I remember those diagrams work is that yes, the variable should represent this UCAP diagram, right? Let's try another one example, a more complicated one. Like, yeah. Before going to this 2 lambda, I guess let's try this one. This is just well, we can't, right? In a way, it's almost like, well, we can make it less like just another nesting of the lambda. So this is like, you already see inside that this piece, right, which is just the identity lambda, so it's here. But now it also, there's an outer lambda. So there's a single input, but the variable is not bound, right? We never use the variable to this lambda. So there's no cup representing it. So that's why it's missing. There's only one, the one that bound to this lambda, but there's no one bound to this lambda, right? If you actually use that additional variable, okay, like in this, there's going to be application created, and now we have two variables floating around, and then there's a replication, then there's an input, and all that, and you like can make these diagrams as a graph. But when you construct it as a graph, then it's like becomes interesting, because essentially, in order to reproduce this example, right, you do the graph one in the diagrammatic computation packet. You can arrange it. Maybe it's a bad name, and it's going to change it in the future. But what I call arrange is essentially take a network, this graph representation of the diagram with all these nodes and wires, and try to arrange it in a grid like that. And it's going to do it like this. So, right. So that's where all these dividers again are introduced. And you can also see there's also another convenient function that tries to decompose it. So now when you have a network, when you just have a bunch of nodes lying around, and you only know how those ports of those diagrams connecting together with wires, if you decompose it, you just have a list of this, right? And you can even take this list and make a diagram network again out of this list. And you basically can reproduce the network back. So in a way, diagram network is just a list of diagrams when there's some information that this ports and this ports are identical. That's how it knows to create a wire there. So in a way, port identity is still this data structure, how the wires are created, right? Right, so, and then the arrangement, but when you arrange it, it's now agreed, and if you try to decompose it, actually it's still gonna have the same number of diagrams like here. Like in the network, it was just a list. They basically there's no composition, explicit composition of these diagrams happening, right? We just have which ports have to be identified. But when you arrange it now, this decomposition returns some kind of structure. You can see that these two diagrams are actually in a product, in a monoidal product. So if you make a diagram out of these two, like that, they just horizontally composed with each other. Now we have a new diagram with these two cups just in a row, right? And this composition, this is circle dot represents a composition. So if you take this piece, for example, and try to compose them into a diagram, now they vertically composed. So it's a vertical composition. You should read it like this is like lambda A after lambda B after this application, right? So in a way, the last one in this circle dot composition, it's the usual meaning of the composition comes first if you read it from top to bottom, right? Right. Yeah. So that's and then you can like take this thing and this thing and compose them again together. We have more convenient names like column diagram, example. So this and this. So it's like a column. So it's like in the conventional use case of Wolfram language when you want to make a column of things, you do it like that. But here you have a column diagram when you want to make this one, and the next one after that, below it is this one, and you compose it and you get a new diagram. So it knows how to compose them together like that. Right.
Connect the appropriate wires with each other.
Yeah, there's some weird tagging of the ports happening. I don't want to discuss in too much details, but it basically, because you can see visually there's like maybe there's some ambiguity, like there are two A's, all right? Which A goes to which A?
Well, they're oriented.
Which B goes to which B? Yeah, well, sometimes it's even orientation maybe still look the same, right? The orientation may be the same, the label may be the same. It still should know how to compose them together. And if you like try to, for example, let's actually try that. Let's just make an arbitrary diagram AB, right? And after that, we make another diagram B with the input B, right? So they compose together. But what happens if there are two Bs, right? It just picks a random one. Well, not the random, just the leftmost usually. So in a way, like if you compose it this way, it's a bit ambiguous which port it should connect to. Of course, there are some rules so that it's deterministic in a sense. But in order to be explicit, what do you want and which port, maybe you should rename it. Like you can rename it. You can like rename this to B1 or something. Now it just flips to this one. Another way you can just do. You can do the product, right, with the identity. You can specifically specify that there's an identity diagram on the left. I wonder whether this works. No, so I just turn it into diagram too. Like that. Hold on. B. Oh yeah, I should have put it here. Right? Why it didn't connect to that? There are too many B's. I would connect to the first one. Right. for the thing I actually wanted to do.
Does the
If I
identity
want,
that has an input, right? Just like connects B to B, connects an input B to output B.
if you make a column, then yes. There's a list of inputs, list of outputs, and it's gonna do. Yeah, basically, yeah. That's what I wanted to show. If you want to, without renaming ports, to be more explicit which ports are connected, you can explicitly put this identity here, right? And now it's gonna be in the decomposition on the of this diagram on the left. If you haven't done it, there's still gonna be an identity, but it's gonna be on the right here, which would be put there together automatically. That's what column does, right? And that's actually the difference between column and things like diagram composition or right composition, I guess, in this case. It's still going to be shown like that with the identity, but it's not going to introduce these identities automatically. It's just in a way that column, in a way, arranges this into a grid automatically by inserting and splicing these identities and permutations. But let's get back to lambdas, I guess. To make it more, you can rotate it. I think that's what we were getting when we just calling this function from the block, right? That's essentially what it does. It's maybe putting some extra options on top, like maybe hiding some labels and all that, and maybe realigning it. I think it's using alignment center. Yeah, so it looks like that. Yeah, so that's our string diagram representing lambda. Okay. So what can we do with it? And I recently have made some progress and actually incorporating in this Parklet rewriting using our hypergraph rewriting package is like another Parklet that we have to have a most general, as we understand it, rewriting of hypergraphs. But I've tried to use this generality of hypergraphs and use those as for these diagrams. And I have some couple of examples. Actually, let's see. I had this couple of helper functions that I haven't put in any Parklet yet. But it's just for convenience. For example, if you want to make a lambda, like this is the simple string diagram for identity lambda expression, right? Which contains this U-turn. In a way, it's just a way to extract a single lambda, like this. In a way, I didn't have to do it, but because there's no way to make this particular node on its own, you can just make this one, ask for what kind of subdiagrams this diagram contains and just take the first one. So that's what our raw lambda diagram is. And we want maybe perform some replacement. For this one, we also rename the label. So here, this diagram expression is placed from here. It's basically maps over all subdiagrams and replaces the underlying expression, which is the label. Maybe in the future, this thing's going to be called data. It's like each diagram contains some data in it, which is completely arbitrary expression. That's why it's called expression, but maybe it should call diagram, data. Like here, it was A and B, those are data, but it can be not just letters, it can be anything. Here, just some kind of rendering from lambda. But if you create some pattern expression, for example, you replace this A here and replace it with the X blank. So now it's more looking like some left-hand side of some rule. So we have lambda that can be put into some left-hand side of some rewriting rule, right? And the second auxiliary function tries to make some specific rule. Let's actually try that on that lambda thing, right? So now it takes this rule and turns it into some empty box, but preserving the wires. So basically what it did here it made a singleton diagram with an empty diagram inside, and just putting the ports of the diagram you provided on top of it, so that now this looks like this. Right? Maybe I don't know whether I should talk about these frames. They're also a nice feature of the diagrammatic processing that we have. Let me show quickly what these frames actually do in general, because maybe it's unclear why that's rendered here like that. But let's see what a singleton diagram says. Is the simplest case of those. So for example, if you have an arbitrary diagram like this, ABC, okay? It's a diagram node that has some input, has some output. If you want to wrap it with another diagram, because the structure of the whole diagram is actually hierarchical. Like this grid of products and composition, they contain a bunch of nodes composed together in some way, right? But when you want just minimal hierarchy in a way, just to wrap arbitrary diagram with another diagram that has different ports, that's what singleton diagram essentially should represent. So it's like a single box around it, right? You can change some ports for it. For example, now it has a X and Y output, maybe, and some Z input, something like that. So that's the box. Okay, and that box can be used in all the other compositions above, like in the product and compositions. But this inside diagram is now untouched in a way. It just sits there. Those ports are completely ignored, but they can technically be connected. For example, this A and Z are different, but I want to maybe preserve it, and now we have a wire between them. Okay, so in a way you can create a new port, or you can like keep the connection inside of the singleton of the box, right? If they're the same, then the wire is there. If they're not, they just wrap around it and create the port. And that's what this right-hand side of the rule essentially represents, is just a box with an empty diagram inside and preserving the rule. That's how we can represent the deletion of this node, or maybe some arbitrary sub-diagram. You just maybe want to preserve the structure, like if you take this one and you want to find some particular sub-diagram inside of it without like worrying about how the wires are being composed together. You just want to the composition. Like we're gonna
It's
go
making
into
black
that, but now
boxes basically.
it would just replace whatever diagram is on the left with this box. Yes. It doesn't have to be a single node, but we'll just try it with a single node first, which hopefully works because it's just new development. So let's just apply. I have a, how's it called? The diagram replace list. It's a list because there are multiple matching that can happen. So it's an analog of replace list in the Wolfram language, right? It also takes some rule, but the result is the list, always a list, because it presents all possible ways the rule can be applied and the rewriting happen. So here's the same thing, right? We have a rule, we have some input diagram, right? And it will try to match it, and hopefully the result should be obvious, right? It just replaced all the lambdas, well, not like in the single way, but it found two instances and removed them independently. So now we have two possible rewritings happened, right, by removing this lambda. So, right, and just let me show you some underlying mechanism of that, how that actually is done. Here it's also introduced some weird tangling, which hopefully sometimes goes away if you rearrange it. Well, maybe not this time, but yeah, there's some underlying algorithms that are very convoluted, how to make it these diagrams by default as less tangling as possible and all that. Actually, let's see, is it correct? There may be some mistake here. It's like, why is it starting doing? It maybe matched some ports incorrectly. Doesn't look like it just removed it, right? The connectivity. Oh, it just started. Yeah. I guess this thing has to be switched. Those caps switched around, right? That's all that changed. Like this and this.
Oh, the A's and the B's
switched places.
It's like,
Yeah, those variables. if you put this one, this turn here and this one here, I think that's gonna be the same as here. I don't know why it didn't do it automatically, but whatever. There's a actually let's try it. There's some magic options that might help. No, not today. Yeah, well, let me show what actually happens under the hood. I have some convenient options to do some exploration. For example, instead of performing rewriting, you can return hypergraph. So that's the underlying hypergraph for the input. So this diagram, I think I have a function that turns this diagram into a hypergraph. Just
Now
to
then,
see
are
what
these
happens.
hyper
So,
edges oriented?
yes, they're directed because the ports are oriented. The ports are in some particular order. I'm assuming, I believe, like inputs first, then outputs. Maybe you can do it the other way around. But yeah, sometimes outputs before inputs are more convenient. But yeah, you just orient the edge. So you turn each subnode of your diagram into an edge, right? And if the ports have a wire between them, that's just the vertex, right? And the hypergraphs naturally now overlap. Edges in the hypergraph overlap. I also put the labels back in some specific way, because when you turn your node into the hyperedge, you actually lose the information about how many inputs were there and outputs, right? Because hyperedge is in a way just directed, but you can want preserve. And that's what this overscript and underscript represent. It's how many inputs were there. So I just put it in the label for now, just to not to confuse the rewriting, because sometimes I found that there are some cases when you have a rewriting rule and without this specification it can apply in some weird way and just tangle things up. So this labeling is actually important.
Right. So the
But now
it's on that first triangle. Let's see, for lambda A, you have like a hyper edge consisting of a. What I don't know what those vertices are, but it's like, let's say the top one is A and the bottom one is B and the left one is C. It's like A, B, C, like that. So that's a 3-element hyperedge, and it's oriented in the sense that order matters on those 3 elements. And so that's why there are arrows along those first 2 edges, but not on the third one, because the rendering
no, this is actually. Well, the oriented is just that's how we're rendering our directed edges. If you do this 1, 2, 3 and make it by default, it's not oriented. That there's no out. But if you say that 1, 2, 3 is oriented, or hold on, edge symmetry. I'm confused. Okay, directed.
Yeah.
Not oriented. So I think oriented was supposed to work too, but whatever. The way we show it is by only placing 2 arrows.
Okay.
Right, in the order of appearance, because there is some particular cyclic symmetry that we also have to distinguish, right? So if it was a cyclic, then we put an arrow here. But if it's just oriented, the direction matters and nothing else, then it's just 2 arrows like that. And the size of it also changes, so that you can immediately say where the beginning is. Like if you put some more vertices into it, can say immediately it starts here. Okay. So this is basically what happens here. You can say that this port here, this vertex corresponds to this wire, because that's the only one that connects lambda B and lambda A, right? And this vertex represents the application. And you notice that there's no wires, right? The only subnodes of this diagram are only 3 edges here, and everything else is wires. So they got completely diffused into this, scattered, whatever. There's no edges representing those wires. And the way this happens is, of course, like the same way how we turned the network representation of the lambda into this grid, you can also turn it back. Like if you turned it to a network, right? By default, it's gonna include those extra wires as explicit vertices. Right here, this is a graph basically, but all the each vertex represents some original sub-diagram, some node of this diagram. So that's why there is some like sticks in there, which are identities, and all the caps in there, and even the permutation is a vertex. So this is just a very fancy rendered vertex, right? So it's not like a weird edge. It's just a vertex here, vertex here, vertex here. But then you can, when you have this graph, it's simple to perform some like simplification of that. You can like right now just like one way of simplifying it by default is just removing all the wire looking diagrams from it and reconnect the ports. Right? That's what simplified diagram is gonna do here. It just removes all these wires, actually put them side by side. All right, so this is basically the simplification of this string network, string diagram is the one that dropped all the wires and reconnected all the ports. So this graph only contains 3 vertices. Well, maybe 4 if you include this free one, but this one is just for convenience here to always show the arrow, but it doesn't go anywhere. It's just like an unconnected port over there. Okay. So, and then you can arrange it back to get the diagram if you want and things like that.
Can we see some like beta reduction, like a sequence of lambda diagrams undergoing computation, and then see like what the trees look like, and that representation, then see what these diagrams look like under that representation, and maybe look at the hypergraph versions as well.
Well, let's try to find some good example from the blog, for example. Okay, evaluation of lambdas. So what's how about that one? Simple enough. Okay, let's start with this one.
That one.
So, oops. So we have the sequence of lambdas. Okay, so I don't like these boxes, but whatever. So let's just call this lambdas. So we have lambda tree. That's what will immediately in the block. We have Trom diagram, this weird labeled way, and we have string diagrams. Maybe that just make them smaller.
What's that triangle?
Oh yeah, we haven't introduced that one yet. The triangle basically represents the copy. So this first lambda was what? There are 2 arguments, right? One applied to itself. So if you have this particular, if you just take this one, make a string diagram out of that. That's how we show, in order to split the wire in 2, we introduce this extra node that does it explicitly. If you have more applications, it's going to have more wires.
Yeah.
Right. So it's like a copy, multi-copy.
Can we see this as a tree?
As a tree, it would be like that.
Okay, so this lambda is saying I want to make a tree structure with 3 nodes and take one input and put it in those 3 places.
Okay.
Yeah.
We also had some different representation. How is it called? With wires like this, right? In a way, it's we called it loopback graph. Okay, we just called it. It's almost like pre-string diagram representation. It's just make a tree and show this extra connection from the variable to the lambda it binds to. So from this representation, I should have showed it immediately, I guess, because from this representation, it's immediate what the string diagram is, right? It just turns this like 2 types of wires into this U-turn, and that's what the resulting string diagram is. It's just it doesn't have a copy here explicitly, but yeah. This is one.
Yeah, now I get it. Thank you.
Okay. Problem. So there's still two applications here. This is one. This is like, because it's just the same variable. Here it has three cups in a way, but this we just merged them into one, but with this extra copy one. So that's what the only thing that changed. Okay. So that's the sequence, right? So that's the beta reduction sequence. So let's see whether we can understand what happened. Let's again look at the. Was it the beta reduction? Oh yes, it was. So that's our lambdas. Right, so that's the 8. Maybe we can, for convenience, we can do variable form. So that it also looks as an expression like that. So that's how I can, so first we reduce this application over there. So that represents an application of this lambda with its whatever its body is to this argument, right? So, and because it's a this copy, this is inside, there's an application of this. Well, just makes two loops because it's you copied the loop twice, and now you have a new diagram where instead of this double copy, you make two loops because it was an algorithm. So something like that. It makes sense. And now you just apply loop to itself. It gets reduced to a loop. Identity applied to identity. So yeah, if the string diagram somehow make beta reduction more apparent, sure. But maybe not that much.
Well, definitely.
Are you also
Yeah, just having a separate representation of the same information is always helpful.
Yeah. We can try making like an explicit rewriting rule, because I haven't done it yet. So we have this simple remove lambda rule. Yeah, right. Actually haven't finished exploring what actually happens under the hood. Like we have this hypergraph, but we also, let's finish that. And then we're gonna try to make a rewriting rule for beta reduction, if it makes sense, as a live coding exercise. So let's see, let's continue looking at this example. So we have, so this is like hypergraph. We can also look at what happens to the rule. So the rule is also turned into, well, it's turned into two hypergraphs essentially, but it's a separate hypergraph rule object. And then we can, our hypergraph packlet is essentially works like that. You have a rule, you have a hypergraph, you apply one to another, and you get some like a bunch of information. Okay, and in that case, you get some association when there's an output hypergraph, and a lot of information what actually being matched together, which vertices being deleted sometimes, which edges being matched, which new edges were introduced. The mapping between, you can see there's a very nasty tagging going on for each port. It's like in the labeling you always see like just A or BA or lambda B, but there's also some extra my coordinates I put there in order for them not to connect together unnecessarily, because you have to track the connection carefully, especially when you go back from grid to network and back to grids. You need to, in a way, remember or maybe reassign the new coordinates so that there's no incorrect connections being created. So that's what this extra coordinate is representing. No, it's like a coordinate in the grid or in the network. There's some bindings. This is just from this point is just a hypergraph rewriting how we defined it. And then the last step, I guess, it would be just take this output hypergraph and somehow match it back to the diagram. So we get the output hypergraph, and then you need to, because you know this rule, right? Let me show it back. So you had this rule. You somehow need to take. Here's the match. Did I remove it? you have to take this output hypergraph and somehow find where the new edges were created, like something like that. There's like one edge being created. That's the one corresponding to this diagram. So you have to match the ports to this structure and recreate the diagram and basically glue it together again into a network. So it's a bit complicated, but at the end of the day, that's what you get, the new diagram, which you can again rearrange into a grid or into a network and work with it like that in this fashion. Okay, I'm sure that it makes sense. Any questions? It's like this hypergraph writing may be complicated.
Can we see a sequence played out in hypergraphs, a beta reduction?
Like for how each individual lambda, how they look like hypergraphs.
Yeah.
Right? Yeah. Oh no, we have to do lambda string diagram. Something like that. Okay. So those are the hypergraphs.
And you were talking about replacement rules earlier. So is there a way to encode this beta reduction as a hypergraph rewriting operation?
I actually haven't thought about it yet, but I think that's what we can try to do it right now. I don't know. It
I
should
don't
be.
think it's directly possible in the usual way, right? Because normally with hypergraph rewriting, the way you define it, it's like you take hyper edges that have a certain size and you replace them by some other hyper edge, right? But here, like the hyper edges can have arbitrary sizes, I think. So that, I mean, like you could have a hyper edge use that contains like arbitrary numbers of vertices, right? So then basically your set of hypergraph rewriting rules would have to be infinite to make it work or not.
Well, that depends on how general your implementation of rewriting. And in a way, our hypergraph, we also try to generalize it, and actually, recently I also made it this arbitrarity also work. So
Okay.
if it requires, if the beta reduction rule would actually require arbitrarity, we can make it work.
Okay.
We have like do you have some example where it's maybe whatever. I can try it, make one. In a way, for hypergraphs, because I have this. Let's try making a rule. Why is it so big? Would that work? Let's temporarily make it a little smaller. It's a bit glitchy. Okay. So if you just have a single edge like that, I know that it's really not compatible with light. Okay, close your eyes. I'm gonna make it, let it be light. I shouldn't make it more compatible with dark mode. But yeah, so if you have like a single edge, I made it work so that if you make it specific label look like this, like a double underscore, or use or like pattern sequence, blank sequence, maybe named one, like maybe X blank blank. If you make this your edge like this, right? But on the left hand side, right hand side, maybe like make a some new vertex with a binary edge created. Maybe you have to relabel it probably because now it's a right hand side. So, for example, if you take this rule, in theory, it should be able to be applied to arbitrary hypergraph edges. Like if you have a ternary thing going, it still would match it. Well, in theory, I said. I think yeah, there's some caveat because it also like implicitly matches, like verbatim matches the symmetry, because the unary edge here has an empty symmetry, but this one is like unordered. I think you can either make it unordered. Let's actually make it that instead of some extra option. I think if you do it like this, stay there, maybe that would work. And not to debug it. So this is like what it tries to. Oh, it has some weird. Well, it's fine. Oh, because this one has labels. It has labels.
What is that number on the vertex assignment? Don't tell me that's your module number.
Which number?
At the bottom?
This one?
Yeah. It's
No,
just like a
this
unique identifier somehow.
something like that, but it's not like a random one. It's like hashing. It's like a hash of something.
Okay.
That's why it's so big and ugly. So I had to do it more or less reproducible. So I wanted some random but unique. So that's why I hashed it against
Should
the
upgrade to
corresponding label.
SHA 1024 or something. That way it's like this huge.
Yeah, no, I think it's just built-in thing. It's like arbitrary expression like that. It basically have the same integer size. Right, let's try this. Is this looking? Nah.
But aren't you trying to match like unary edge and you don't have any unary edge on the right?
Well, that's what I'm trying to do. I'm trying to make arbitrary arity work. Okay, so this like this label, because it has this underscore. Oh, hold on, maybe I just labeled the wrong thing. Oh no, that's edge label. It's fine. Just vertex should not be labeled. Yeah, I don't know. I know that there's a. Yeah, there was some caveat I already forgot about. The idea is that this turns into this thing. Oh, it's not. Doesn't look correct. Maybe I have old version. Oh, why I'm labeling edge? Right. So edge is just any edge. It can be like whatever. But the vertex should contain this thing. Maybe that's the correct way. I already forgot how I coded it up myself. Okay, that worked. Maybe that's not required. Yeah, you see? So now this one, even though it's a unary, it matches against this one. If I put some binary here, so that it can also match that one. And you need to be oriented, ordered. Yeah, so now there are two matches. So here we basically attached a binary edge to the triangle. Oh no, hold on, what we did. It's a, what's that thing? It's hard to say whether there's a two edges or not. Maybe we should remove. Well, anyway, you can stare at it and then try to understand it, but that's what it does. Currently, maybe it can be better, but the idea is that to some degree, I'm trying to make arbitrary arity work, and if it works if it requires for better reduction, then we can make it work probably. So let's try to figure out how
So
to.
I guess like there would be a need for annotations on the hyperedges, the vertices of a hypergraph, and some ordering on the hyperedges to make beta reduction, to interpret these hyperedges as lambda diagrams and then do beta reduction on them, and to compose them and stuff. If it's
Yeah.
possible, right?
I think it's possible. Just let's try to figure it out. So the idea of beta reduction is like, maybe you have some body, you have some argument, right? And you need to, if you make a lambda string diagram of this lambda b, apply to x. So that's like a minimal thing. We should just replace this by some arbitrary thing that can be matched against, like a, right? It's probably, it's always going to be a loop, actually, right? So in a way, this is it possible to make it like more apparent. That's like a something with some attachment in there. So it's like a body here, right? But in the end, we can, our left-hand side should look like take this. Let's try to construct approximately at least how the left-hand side should look like. Got this diagram expression we place above when we created lambda, like this, right? So that's, for example, would allow us. So that replaces this lambda a with some arbitrary label. So that's definitely right. Right. So, but we need to replace x. Maybe we should just drop the lambda. And, for example, just don't care about those. This is the pieces that we need. It's like, this is our lambda. This is the copy, the application. This is the app. Okay, so in a way we can construct something directly from those. Maybe it's like I still don't have like a good experience doing it myself. I have a framework. I don't know how to use it. So that's been it's like a little, definitely like a column. Want to rotate, so it looks like I guess the same stuff. So that's our like top thing. So we can ignore all these weird things. In a way, this is always the case when you have a beta reduction, I guess. So that's like the minimal thing. Some lambda, something is being attached here, the body, right? And this is the argument. So in a way, that's the, we just need to put here something that can be representing the whole thing. So what's the port? Let's actually make some argument. The up. I think it should be. Let's make it a product more explicitly. It's like a lambda. To the right, there's an argument, but it has a port. The application have input ports like this. That's this X. We can take this X, whatever. It's too complicated to an X. It has some weird. It doesn't matter what inside of it, but yeah. Okay. Let's put it on the right. Hold on. Just make it the same. Okay. It's weird that it's tangled. I think you can allow for it to sort out. Yeah, there's still some bugs in there, but it's gonna intervene. And something like a body. Like this argument is actually just like an actual pattern. I wonder whether when I do rewriting, I actually don't allow each diagram would turn into an edge, but that edge should be allowed to match against multiple edges. So in a way, we're not allowed to, or we have to put. We're not allowed to put anything here, or we have to represent it differently. Like the current scheme is always performs this one-to-one diagram node to an edge. But if they're in the pattern, we need to be able to represent with a single pattern that match multiple edges, right? Yeah, that's more complicated. I'm not gonna solve this now. I
No,
realized.
no, it's just
Yeah.
spitballing.
But that's like at least the problem is more apparent now. It's like we need this ability to match, and that's what I actually was hoping to understand what I should focus on developing next. So I was trying to make this multi-port matching, multi-vertex matching work. That's kind of okay-ish. But here is like multi-edge matching should be also more usable. And then we can think about how to do it, the better reduction.
Can we
But
see
you're
some
right.
more examples of like more complicated beta reduction and look at tromp diagrams and string diagrams and then like tree diagrams?
Yeah, I have like example, a more bigger one. For example, like this is some large diagram,
Mhm.
right? For example, if you want to replace some subdiagram, so the subdiagram that you want to replace, for example, is this, right? In a way, you can find it, like here, right? This part, lambda C, right? But it's like completely different wiring,
Mhm.
but you want to replace this part. So you can create this remove diagram rule from subdiagram. So that's the rule. And then you do this diagram replace list in the diagram. Hopefully it works and creates this empty box here. Okay. So that's worked. So that's replaced all this right appendage to this lambda C
Mhm.
with this single box. So this removing of diagrams like works nicely. So then it depends, of course, what your right hand side is. It can be more complicated.
So that's just reducing like a sub lambda expression as like a little box, a little black box. In this case, a little
Yeah, that's what it does.
little dotted
Okay,
black
but
box.
we could made like a more complicated expression here. As soon as like the ports are more or less the same, so that we can reconnect it properly.
Yeah.
But I didn't have to like look exactly like this because the underlying writing works on the level of networks and graphs and hypergraphs. The grid here, the grid representation and this composition is just an extra thing. Okay, do we have more examples? Yes, I haven't done like a lot. That's basically like it. I have like a non-lambda related example. Maybe I can show that. Have this example here, just a row diagram,
Mhm.
nothing to do with lambdas, but you can create two kind of rules. It's more algebraic, like this associativity one, which takes this associativity in terms of those input ports, right? You know, it's like you put your F is like brackets. here it's around P1 and P2, and here it's around P2 and P3. And another one which is just reversed. It's the same one but for output, right? And in this input diagram, you can find those in two places, right? Here you can apply associativity rule, and here you can apply to A you can apply associativity, to B you can apply co-associativity. Yeah, so that should work. So if you apply this one, just make it side by side. Did it work or not?
Looks the
No.
same. But yeah, do copy that and place them side by side.
No, I think it didn't work.
So there's
Depends
no
what
associative reduction on that.
no, it's something else happening. Let's see. Diagrams. I may have broken it somehow.
Well, no one else would know. So
Yeah. So that yeah. I think I broke that example. But I have I saved the output at least. It should look like, if you apply both rules, it should look like this. Let's pretend that it worked. Okay, just some late development back. So that's what B and A got replaced slightly. Just shifted around. Okay. When you do it, because you can like debug it and all that. Try to see what's happening with hypergraphs. And that's the problem. I know what's happening there. It's not passing. There. This work. Yeah, something happened to application. Those labels. Oh, those labels. Look, I shouldn't attach the labels. I think I should carefully remove the labels everywhere. That's what I've changed. I remembered. Because I now map the labels. I have the port labels. I just need to hide them. They kind of have to become invisible. I don't know how to solve this problem, but let's try with it. If you apply this now, something happens. No, right? No. Or is it still there? Maybe this labels. Anyway, it's the right to hide it completely. The problem is that P3 belongs to an identity. It's turned into a network. To put some label there. Anyway, yeah, I was messing around with labels, and I think I broke it. That's why. You're just not going there into there.
I like how the label on F was also rotated.
Yeah, that's yeah, it tries to preserve the same orientation with inputs and outputs. There's some cool styling you can do. Like F, A, B. If you make them red and you do some composition with another diagram. Like G, B, C. Like if it doesn't have a style, it's gonna inherit it.
Yeah.
But if you have a style, I think it's like double colored or diagonal. That's what's different from edges in the graph, because you have a directive and styling belongs to a port, not to a wire. So in a way, it's like has this double direction. So in a
I
way,
see.
that's what I decided to do when they not match.
So there's a little point in there where they have to match up. Oh, it split it into 2 segments. I see.
Yeah. It puts it in so that you can see that there's actually 2 ports and they style differently. Only if the styling is compatible, it can merge them together.
Mhm.
So you don't see that. And it should work. And this propagates into the graph too, I believe. Just becomes a bit ugly because it's like 2 independent edges.
Yeah.
Yeah, I need to think about how to make it better rendered. Yeah, I guess that's it. It's like we explore the string diagrams a bit.
Yeah, that's amazing. Really good technology.
Yeah, I realized what else to do, what kind of new problems that I haven't even considered yet there. It's
Can you
cool.
make a causal graph for a lambda calculus formula?
For the beta reduction?
Yeah.
Yeah, we had it in the blog, by the way.
Oh, okay.
We had like the whole chapter on causal graphs somewhere at the end.
Ah, cool.
Let's see. Oh, this thing is there. Causality of lambdas for lambdas.
Okay, nice.
It's like the whole causal evolution graph. So it's like events here show the beta reduction happening.
Ah, okay, yeah.
Wait, so
And-
is beta reduction is it uniquely determined where a beta reduction would take place inside of a big expression, or is it like you have an expression with a bunch of lambdas and maybe you could beta reduce like the top level or the bottom level, and
yeah. If you just given an arbitrary lambda term, there are
Mhm.
multiple positions that beta reduction can happen, and
Okay.
depending on which evaluation order you use, you can do it in different order.
Yeah.
But when you want a causal graph, each lambda can be like if they're spatially separated somehow, each event reducing one lambda subterm can be completely independent of another, and that's in causal graph would be represented as the like space separation between
Right.
Yeah,
events.
so there's like a unique causal graph, right? I guess. I mean, there's not like multiple causal graphs, basically. There is a way like to get the unique causal graph, right?
It's like a multi-way causal. You can make a multi-way causal graph when you try to enumerate all possible orderings and then merge them together. We also have those. Like these causal graphs, they are created for a particular order. So it's like in the Wolfram physics terminology, it's a single-way causal graph. So you reduce the lambda in one particular order so that you know which particular events you executed, right? Which
Ah,
beta
okay.
reductions took place. Each beta reduction is a separate event in the graph. And then you just connect them depending on whether they're dependent on each other, whether they somehow overlap, they not in position, but also in whether they use the same variable, something like that. There's some criteria to determine whether the two
Okay.
events are dependent or not.
Yeah.
But you can
Now,
enumerate all possible orders.
is there
and do like-
necessarily confluence in the manner in which you apply beta reduction?
Well, confluent in a way that you always lambda calculus is confluent. So if it terminates, you get the same lambda at the end, right?
Okay.
But the causal graphs can be different, so they're not isomorphic for different for different ordering. Like here, I think
Yeah,
it's
you
like
can apply beta reduction in different orders, but in the end, once you do all the beta reduction that you can, you'll have the same result from the same starting condition.
yeah. Same result doesn't necessarily mean that your causal graph can be the same. It's going to be they're going to contain a different number of events even.
So that
Obviously,
is to
because
say
different
that the beta reduction is a let's say associative operation.
Well, maybe I don't know, commutative. I don't know.
Something like that.
So the causal graphs can be different depending on the way in which and the order in which you apply the beta reductions, but all of the causal graphs will have some resemblance to each other, such that basically they kind of give you the same end result, I guess. Like
No, they wouldn't necessarily resemble each other. They can be, because orderings can be, like we had this chapter on how different order differ from each other.
yeah,
For example, like look, it's like, for example, so one order can go like can not even terminate,
yeah,
right?
yeah, true. And another
And
one
one
is just like
can skip to the result, and
yeah,
in different.
exactly.
So this
So
is
you
like
can
a
have
one-shot causal graph, which like with two events, and this is just like non-terminating.
yeah, true.
So they can completely be different from each other.
Yeah,
Yeah. But you can enumerate all of them and make this multi-way causal graphs, right? So we can construct the whole multi-way graph for all possible reductions in all possible orders, and then for each path, in a way, construct a single-way causal graph and take some sort of union and just create this monstrosity like this when they're
yeah,
just overlapping.
But the causal
Yeah.
graph, I mean, we say that the causal graphs might not be isomorphic. Between what? I mean, if you start with a lambda expression up top, and then like you apply beta reduction in all the multiple different ways that you can do that, then you have a multi-way graph, right? A causal graph, and then that'll look the same based on what your input expression is, right? Like, I mean, is it deterministic? You have an input expression, you have a multi-way causal
Yeah.
graph for that. You'll have a graph for that, basically.
yeah. It's basically because
I mean-
one part of the expression can delete some other part. So if you just delete it right from the start, then you have you might have a very simple causal graph. But if the part that you're about to delete, if you just let it run for a long time, then you get some more complicated causal graph, I guess. Maybe that's why you can get like different, completely different looking causal graphs, right?
Yeah, because I think this is even the example. Like this is, you start with the same lambda, you end with the same lambda. You can take multiple different paths. You can go like from here, you can go from there, right? But
Right.
depending
The
on the
path,
path, you accumulate different events, and you have different causal graphs depending on which path you take. So, and they can be completely different.
well, those are different graphs for different expressions.
Maybe not. Let's take a look. I don't remember because
Yeah, one has to probably add some extra condition of some sort to make it such that all the causal graphs would be kind of similar, such that you can you can find some kind of rough isomorphy between them and all that stuff. Yeah, but I don't know exactly what the condition is.
Well, here this causal graph is saying that given the input expression up top, there's only like one way each time to apply beta reduction.
what do you mean each then? Why in this one? Yes.
Yeah.
So this one is boring.
Right.
Like this is more interesting. But it's like for the single way, here it's like a multi-way. It's already the union. But if a applicative, okay, this is like a good example, yes. So there's normal order and there's applicative order, and they produce completely different causal graphs. Right.
Okay, so that's a traversal order on on how the beta reduction is applied. I mean,
Yeah.
why isn't it just look at all possible ways to apply beta reduction for each node, and then you make this big graph, and that should be all inclusive and sort of you won't get multiple different versions based on what particular method for
Well,
investigating.
that's what this multi-way. That's what multi-way causal graph is. Okay, so this is like a
Right, so
just
that's the
causal
biggest
graph.
one that includes all the other subgraphs that you want to look at.
Yeah, this is like the union of all these possible paths that you can take. So all
Yeah.
possible events that are there, all possible events that can happen during reduction in any order should be present in this graph.
Okay.
Okay.
Very cool.
What else did we have here? That's cool. Yeah. Well, I guess I have nothing else to tell you for today.
All right. Thank you so much, Nick. Thanks for everyone tuning in on the live stream. We'll see you again next time.
See you. Bye, everyone.
Cool. Bye.
Thank you. Bye.